Although a random variable may seem to behave in a haphazard or chaotic manner to us, statisticians have found that these variables follow certain patterns and that the behavior can be captured in models. These models are called probability distributions, and they can be represented by formulas, graphs, or tables. Now, because the two types of random variables mentioned above are mathematically different, one being continuous and the other being discrete, we need to have two different types of models. Discrete random variables need a non-continuous distribution. This is known as a probability mass function. On the other hand, continuous random variables need a continuous distribution known as a probability density function. First, we will look, though, at the probability distribution of a discrete random variable, the probability mass function. Now, just one note. We use the uppercase letter X is the name of the random variable. And little x we're using to take as a specific value of the random variable x. So if x, big X, is a discrete random variable, then a function little p of x is defined as the probability mass function, or PMF, of our discrete random variable. And this function has the following properties. This function p of x has to be greater than or equal to 0 for all values of x. When you sum the probability mass function p of x for all values of x, you will get 1 exactly. And finally, what this means is p of x, it's equivalent to the probability that our random variable x will be equal to some specific value of x. This is our random variable. So we'll look at an example in a minute. Back to our tossing the coins. Let's say we have a random variable x, and we're setting that to equal the number of tails, or eagles, when we toss an euro 3 times. So we can have, in this case, we have no eagles. In this case, we have 1 eagle. Here we have 2 eagles. Here we have 3 eagles. And we can quickly see that we have a possible 8 combinations of results. We can either toss all heads or all tails, or we can toss first time 2 heads and a tail, then heads, tail, heads, heads. In this case, we have just 1 eagle, or heads, tails, 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 heads, tails, tails, heads, heads, and then we have 2 eagles. So the probability of the 8 events then is going to be 1 out of 8 that we get all heads, 1 out of 8 that we get all tails. So 1 out of 8 that x equals 3, and 1 out of 8 that x equals 0. And likewise, you have 3 chances to get x equal to 1, and 3 chances to get x equal to 2. Now, let's look at the PMF for this. So we have the random variable x denoting the number of tails when a coin is tossed 3 times. In a table, x can be equal to, our big random variable x can be equal to x equals 0, x equals 1, x equals 2, x equals 3. The probabilities, we've written down here 1 8, 3 8, 3 8, and 1 8. We can write this in a closed form if we go back to our knowledge of mathematics as the combination from n equals 3 tosses, how many times we get a tail, where so x can be equal to 0, 1, 2, or 3, and we come back to that in the binomial section. Or we can look at this as a graph. So here we have probability of 1/8, here we have a probability of 3/8. And this is our PMF. What we notice about this is that if we sum all of these values, we will get exactly 1.0. We also notice that all of our values of p of x are greater than or equal to 0. And the p of x is equal to the probability that x has the value of a specific number of tails. Now, if we have a continuous random variable, then we don't have p of x, we have f of x. This is the probability density function, or PDF of x, and that's what we use for a continuous random variable. And this has the following properties. Our PDF, our probability density function, is going to be greater than or equal to 0 for all values of x. And if we sum all possible values, which we do, of course, with an integral for a continuous variable, we will find that our total is exactly equal to 1. And what this f of x means, since we have a continuous variable, we can never find the exact probability that will be exactly at a certain value of x. We have to look in an interval from two values such as a and b. And what we're going to do then is take the integral of our f of x from a to b, and that will give us then the probability that x is less than or equal to a, is less than or equal to b, is greater than or equal to a, is less than or equal to b. The probability that x is in the interval from a to b. So such a function, f of x, is called the probability density function of the continuous random variable. So you can see this is analogous to our PMF situation. Here's an example. We have a random variable that is known to have this probability density function. From x is 0 to 10, the function is 0.01x. From x is less than or equal to 10 to less than or equal to 20, we get 0.01 times 20 minus x, and otherwise our function is 0. So if we wanted to draw that, we would see this would look like a triangle. So we have here a slope, constant slope up, and here constant slope down, and 0 everywhere else. So f of x dx from 0 to 20 is going to be the area under the curve over all possible values of x. And this, in this example, is just the area of this triangle here. And so we have 1/2 times the base times the height. And if you put in our numbers there, we get that to be exactly equal to 1. We also say we're interested in the probability that our random variable lies between the values 5 and 10. Then we take the integral over 5 of f of x from 5 to 10, and here we're looking under this part of the curve. So we take the integral over 0.01x, and if we solve that, we find out we have a 37.5% that x is between 5 and 10. Now this is an example. It looks like a triangle. What we're going to do in this course is to use these properties with other distributions. And for the PDF, it'll be primarily the normal distribution. So this is an example just to show you what a PDF means, and the example to show you what a PMF means, and we will build on that from here. So the last term that we need to understand, though, is the cumulative distribution function. When we use mathematical models to describe populations, it's often very convenient to have the cumulative distribution function, or CDF. And this is represented by a capital F of x. The CDF for any x gives the probability that the random variable takes values starting from the lowest possible value up and then 2 including the given value of x. So if x is a discrete random variable with, remember the PMF, the probability mass function, denoted by P of x, then the CDF, it's given by capital F of x, and it's equal to the probability that our random variable is less than or equal to some specific value. And since we have discrete values here, it's just the sum of each of the individual P of x. And you can draw that as a step function. At each possible value of the random variable, you get a step. And if you sum all the values up until the maximum value, you get 1.0. So starting 0. Now for a continuous random variable with a PDF, this time called f of x, then for our cumulative distribution function, our CDF, we still use the symbol big F of x. And we still know that this equals to the probability that our random variable x is less than or equal to some specific value. But in this case, we need to look from the smallest value of x to a certain x value. And we can show this with a continuous function. So this time, we don't have a step function because x can take any value. But likewise, once we get to the maximum value that x can be, you see that this is equal to 1.0. So in both cases, for the continuous and the discrete random variables, for the continuous distribution function, you start with the lowest possible value of x. You look at the probability, either P of x or F of x, and then you start to sum that. And as x gets bigger, you sum the probabilities. And this gives you either a step function for a discrete random variable, which goes up to 1, or a continuous curve. This is a monotone increasing curve for a continuous random variable, also goes to 1. So this is an important concept that we'll also be using then later in the course. So the last topic here is the mean and the variance. Now, a probability distribution function, so the PMF or the PDF, chosen appropriately for a random variable, will completely describe the behavior of the random variable. It will give the probabilities that our random variable is equal to a certain value for all possible values of the random variable. In the case of some distributions, however, the description can be accomplished adequately enough using just 1 or 2 numerical measures. And these measures are referred to as characteristics of the distributions. The 2 most important are the mean and the variance. Now, what does the mean mean? The mean is the weighted average. It represents the center of gravity of a distribution, and it indicates where the distribution is located on the x-axis, where the central point is located for the distribution. So if x is a discrete random variable with a PMF equal to P of x, the way we calculate the mean is that we sum for all possible values of x, the value of x multiplied by the PMF. If we have a continuous distribution with PDF equals f of x, then we do the same thing, except we take for all possible values of x, the PDF times the value of x. So, as stated above, then, the definitions show that the mean of a probability distribution is the weighted average of the distribution or a center of gravity. The variance is the second important characteristic of a probability distribution. The variance is represented by the Greek letter sigma squared, and it's the weighted average of the squared deviations of the values of the variable from its mean. And it gives us an idea of how dispersed the distribution is about the mean. The larger the value of variance, the more variability there is in the distribution. So if the random variable is discrete with a PMF equal to P of x, then you take the values minus the mean squared, and you multiply that by P of x for all values of x. If it's a continuous random variable with a PDF equal to f of x, you take the integral over all x of the value minus the mean squared times f of x. The standard deviation is commonly used then as a measure of variability in quality engineering. And, the standard deviation is equal to the square root of the variance. And this is used most commonly in quality engineering because this has the same units as the mean, same units as the random variable. Okay. So some important probability distributions. In the next section, we will introduce the probability distributions that are most useful for describing random variables encountered in quality engineering. The binomial and the Poisson distribution are probability distributions, PMFs, for discrete random variables. And the normal distribution is a PDF for continuous random variables. There's many other important distributions, such as the exponential, the y-able, the t distribution, the chi-squared, f distribution, and we will see some of these in parts of the course, but we'll have a main focus then on these three, particularly on the normal distribution for our course.